I'm gonna put it on canvas after we finish, all right? So that you, if you miss the class, you can rewatch it. So last time we were trying to solve this equation, all right, on 0, 1. And then we have the boundary condition, the Differential boundary condition at 0, and the Neumann boundary condition at 1. So this is the Differential. This is Neumann. All right. So this is the boundary value problems that we are trying to solve. So we have a Laplace equation. On the right hand side, you have a source term which is -2. You have a Differential boundary condition at 0. You have a Neumann boundary condition at 1. All right. So in the previous step, in the previous class, we said that we have 3 steps to solve this equation. Step number 1, you need to find the eigenvalue and eigenvector. All right. So in the previous class, we have already solved this problem. You have phi xx plus lambda phi is 0 on 0, 1. And then you have phi of 0 is 0. And phi of x, 1 is also 0. All right? So basically, this is the eigenvalue and eigenvector problems. We try to solve with the same boundary condition, which means that here if you have u0 is 0, here you have to have also phi0 is 0, all right? Here you have ux is 1, then px has to be 1, to be 0 as 1, right? So in the previous class, we also found the following things. So you have a class of eigen value, which is n minus 1 half pi squared phi n of x is also sinus of n minus 1 half of x, right? So these are the value that we found, and n is going to be 1, 2, 3, 4 exactly, right? It's clear. So these are the eigenvalues and these are the eigenvectors, right? So these are eigenvalue and these are eigenvector. All right. So which means that if you plug this into this equation, you're gonna get phi n second plus lambda n phi n is 0, and you also have phi n of 0 is 0, and phi n prime at 1 is also 0. All right. So now we are going to move to step 2, right? Step 2. Right. So in step 2, what do we do? So in step 2, what we do is we expand -2 in terms of all of the eigenvalue and eigenvector. So -2 will be fn times phi n, the sum when n is going from 1 to infinity. All right. So and then you also need to so basically this is, so let me continue this one. So this is going to be interval from the sum of n going from 1 to infinity of fn of sinus of n minus 1 half x. All right. So in step 2, you're gonna expand -2, or in general the source term, in terms of all of the eigenvalues. So all of the eigenvalues will form a new basis for the whole problem, right? So now you're gonna expand u. U of x will be the sum when n is going from 1 to infinity of un phi n, and this is also the sum when n is going from 1 to infinity of un sinus of n minus 1 half x. All right.
Do the signs need a pi?
Yes, there's a pi. Yes, there's a pi there. Can you sign and the back of the paper, please? All right. So I explain again. So the first step is one way to find eigenvalues and eigenvectors of the problem, right? After you found these eigenvectors and these eigenvalues, what you do is you use them as a basis for the source term and for the solution. Because they're the basis, so you can expand the source minus 2 in terms of phi n, all right? So you're going to have fn times phi n, so which is like fn sinus n minus 1/2 pi x, right? So fn are all of the coefficients. And un, so now you're going to expand use in terms of all of the basis phi n, all right? So ux will be un phi n, and you take the sum. So phi n is given here. And we have a formula for that, right? So un will be fn over lambda n, right? So in the previous class, you know that un can be computed if you divide fn by lambda n. Script, right? So so why do we have this formula? So I want to explain to you why we have this formula. Right? So I'm going to explain to you, but in the exam you don't have to. You just apply this formula and it's going to be fine. All right? So so where is this formula coming from? So in order to see this formula, you have just to plug this into the equation. All right? So you have what? You have ux is the sum when n is going from 1 to infinity of un phi n, right? So which means that u prime of x will be the sum when n is going from 1 to infinity of un phi n, right? So because you have ux is the sum when n is going from 1 to infinity, so you have so when you take the second derivative of u, you also have un times phi n second, right? Remember that fn, un are coefficient, and phi n are function. All right? It's clear? So now after you have this, right? So you plug it over there, so you have u prime of x is minus 2, but minus 2 is also fn phi n, right? Right, so you take a second derivative of u. You have what? You have the sum when n is going from 1 to infinity of un phi n second. But what is it? This is minus 2 according to the problem, right? So when you expand minus 2, you have fn phi n. It's clear? But because phi n second satisfy this relation. All right? So which means that you have the sum when n is going from 1 to infinity of un minus lambda n phi n. All right? So I explain again. It's clear? Right? So I explain again. So first, what you do is you try to solve this eigenvalue and eigenvectors problem. So you have x plus lambda x is 0 with the boundary condition. So in the previous class, we know that we have eigenvalues of the form lambda n is n minus 1/2 pi squared. All right? So you also notice that the eigenvectors of this form, phi n is sinus n minus 1/2 pi x. All right? It's clear? So these are related by this identity. So you have phi n second plus lambda n pi n is 0. All right. So so now you have what? You have minus 2 is going to be Fn. So now after you compute everything, right? So you have a new basis for the whole problem. All right. So you expand 2 in terms of all of the phi n. So you have minus 2 is Fn times phi n, and you take the sum. So you try to solve for u. So you expect that u has this form, and the unknowns are un, right? So ux will be un times phi n, and you take the sum. So you have to make the relation between un, because this is what you try to solve with Fn. So this is very easy. So you have u, which is of this form. So un are the coefficient, and phi n their function. So when you take the second derivative, you have to take the second derivative with respect to phi n, right? So now you apply that formula. You have un minus lambda n phi n. All right? So now you compare the two. So you're gonna have integral from 0 to infinity of un minus lambda n phi n is integral from n to infinity of fn phi n. All right? So here I have a minus. So which means that un times minus lambda n is fn. All right? So then you have un is minus fn over lambda n. It's clear? Questions? Yes?
Why is phi n the second derivative and then it becomes no derivative?
Why there's derivative and there's no derivative, right?
No, on the bottom.
On the bottom.
The one below it.
This
they're
one?
They're both u prime of x or u double prime of x, right?
Can you repeat the questions again?
So the middle line has
This one, right?
phi double prime, but the third line doesn't have phi double prime. Is that just
So now this is the expansion of minus 2. Right? So we are solving
so are those?
yes, so this is the expansion of minus 2. Right? So this minus 2 can be expanded in terms of fn phi n. Right? And you try to solve the equation u second is minus 2. Right? So there are two terms. So this is the equation. So this is the equation. Right? And this is the expansion of minus 2. All right? It's clear? Questions? Other questions? It's fine. Right? So now you have this formula. So you have un is minus fn over lambda n. All right? So which means that now you have to compute fn using the minus 2, right? Right? So now the next step, the next task in step 2 is to compute fn. So now we have to compute fn. Computing fn. All right. So how do we compute fn? So
You use Fourier's trick.
so you use the formula that you have, which is similar to Fourier coefficient, right? Then you sign it back. So you have what? You have minus 2 is the sum when n is from 1 to infinity of fn phi n of x. All right? So this is what? This is the sum when n to infinity of fn sinus of n minus 1/2 pi x. Right? So we have a formula which is very similar to the Fourier coefficient, which is the following. So you have minus 2 inner product with sinus of n minus 1/2 pi x, right? Dividing by sinus of n minus 1/2 pi x and sinus of n minus 1/2 pi x. So this is the formula, which is exactly the same in the case of Fourier series, right? So you remember, yes?
So like this equation only works if like it's like u is a self-adjoint, right?
Yeah, this works only. Yeah.
So do we have to prove? So like do we have to prove that it's self-adjoint?
Yes, you have to prove that this is self-adjoint.
Okay.
But I'm gonna check that for you.
Okay.
Yeah, right. So I didn't check that this is self-adjoint. I just tried to compute, and you see that it works. But why does it work? It is because the operator is self-adjoint. But I'm going to check that at the end, right? So in the exam, if I don't ask you to check self-adjoint, you don't have to. But if I ask you to check, then you have to check. But this is just one line, right? Can you sign it back? Other questions? All right. So how can we? So I explain again. So we have two steps. The first step is to identify all of the eigenvalues and eigenvectors. So if you have all of the eigenvalues and eigenvectors, you have a basis, right? So all of the Phi will become a basis of the solution space, right? So once you have this basis, you can expand the source term in terms of all of the basis. So Fn will be the coefficient and Phi will be the basis. So Phi are the constant. So then, because all of those eigenvalues and eigenvectors form a basis for the solution space, you can expand U in terms of this basis. So you have U and Phi, and this is the unknown, right? This is the unknown. So U is also the unknown, right? So you try to solve for U, but you can expand F, and Fn are given, right? So Fn are given, because you can compute them. So now you expand U, and you have Un that are the coefficient of this unknown. So Un are unknown, right? So you can compute Un in terms of Fn. So you have Un is minus Fn over lambda n, which can be proved this way. So the proof is pretty simple. So you just expand U in terms of this basis. You take a second derivative, and the key is that you use this feature of Phi, right? So you remove the second derivative because they are the eigenvalues and eigenvectors. So then you have Fn Phi, which is on the right hand side. On the left hand side you have Un minus Phi, so which means that Un minus Phi and Fn are equal. So you identify the coefficient, and then Un minus Fn over lambda n. So the final things now is to compute the coefficient. But the coefficient can be computed by using the same formula as you use for Fourier series, right? So you multiply Phi with minus 2, and then you multiply Phi with itself, and you take the fraction. Right, so what is minus 2 and sinus of n minus 1/2 pi x? So this is the interval from 0 to 1 of minus 2 sinus of n minus 1/2 pi x dx. Right, so this is from 0 to 1, right? So the inner product of minus 2 and sinus of n minus 1/2 pi x is the interval from 0 to 1 of minus 2 sinus of n minus 1/2 pi x dx. So you have to do this computation, right? So, but this is easy. So I'm gonna move minus 2 outside. I have interval from 0 to 1 of sinus of n minus 1/2 pi x dx. All right. So because minus 2 here is constant, I can move it outside. So now I'm gonna take the antiderivative of this one. So the antiderivative of this one is cosinus of n minus 1/2 pi x minus, and I divide by n minus 1/2, and I take the difference between 0 and 1. All right. So the antiderivative of sinus is minus cosinus, all right? And of course I have to divide by this factor, right? So this gives me minus 2 cosinus of 0 minus cosinus of n minus 1/2 pi dividing by n minus 1/2 pi. So you have minus 2 dividing by n minus 1/2 pi. All right? It's good? It's clear? Right, so now in order to compute the Fn, you multiply phi n with minus 2 and you divide that by phi n squared. So when you multiply phi n with minus 2, what you have is integral from 0 to 1 of minus 2 sinus of this thing. So the antiderivative of sinus is cosinus. So I have minus cosinus of 0 minus cosinus of n minus 1/2 pi, and I have to divide by, yes?
Shouldn't the negative sign be canceling out there? Like you have minus cosine 1, 0.
Yes, this is minus. Yeah,
That's also minus.
no.
You just flip that.
Yeah, so this is minus. I keep it. But here you have
Yeah,
minus cosinus of 1 minus.
Okay.
Minus
Yeah, I
cosine.
just didn't realize you flipped the balance.
So I changed that, right? So then I have minus 2 over n minus 1/2 of pi. All right, so let us compute the second one, right? The second one is the interval from 0 to 1 of sinus of n minus 1/2 pi x square dx, right? So this is the second one. So I'm gonna compute this and I'm gonna divide this by that one, all right? Yes?
On the, right before you just went to this step, why didn't you evaluate it at 1?
F1?
Yeah, when you were evaluating the integral.
Yes.
You flipped the balance and you evaluated it at 0.
0, this is 0, right? And this is 1,
Oh, gotcha.
right? So this is when I replace 0, here I got 0. And if I replace 1, I get this.
Gotcha, I see.
Other questions? So this is integral from 0 to 1, 1 minus cosinus of 2 n minus 1 pi x divided by 2 dx. All right. So I have used the following formula. So I have sinus square of x is 1 minus cosinus of 2x divided by 2. All right. So I'm going to continue here. All right. So now I have to compute this interval. So in this interval, I use the formula sinus square is 1 minus 2 cosinus of 2x over 2. So here I applied over there. So the first one will give me x over 2, and I evaluate that at 0 and 1, minus integral from 0 to 1 of cosinus of 2n minus 1 pi x dx. All right. So here, this has 2 terms, and I have to divide by 1/2. Right? Here I have 2 terms. The first term is 1/2. So the antiderivative of 1/2 is x over 2. So I evaluated it here. Now the second term is minus 1/2 of cosinus. So I put it here. Right? So the next step is to do. So this gives me 1/2. This gives me 1 over 2 of sinus of 2n minus 1 pi divided by 2n minus 1 pi 0, 1. All right? It's clear? So this gives me 0, right? So this gives me, the other one gives me 0, so this is 1/2. So it is 1. So this is sinus of 2n minus 1 pi minus sinus of 0 dividing by 2n minus 1. So this is 0. So basically this is 1/2. Alright? Questions? So I explain again. So in order to compute Fn, we have a formula, right? So we have a formula. Fn is the inner product minus 2 and then sinus, which is the eigenvector, and you take the eigenvector square. Alright? So now you take the inner product of minus 2 and the eigenvectors. This is the interval from 0 to 1 of minus 2 sinus of n minus 1/2 pi dx. Right? So I move minus 2 out, so I have sinus. So I take the antiderivative of sinus, I have minus cosinus. So minus 2 minus cosinus n minus 1/2 pi over n minus 1/2 pi, and I take difference from 0 to 1. So this is minus 2, so at 1 I have cosinus at 0 minus cosinus at 1. So this is 0, so finally I have minus 2 over n minus 1/2 pi. It's clear? Now, I have to take the square of the other eigenvalues and eigenvectors, and then I have to evaluate the interval. So this is sinus square. So sinus square is 1 minus cosinus 2x over 2. Right? So this is interval from 0 to 1, 1 minus cosinus of 2 n minus 1/2 pi over 2 dx. Right? So here you have two terms. You have 1/2. So the antiderivative of 1/2 is x over 2. So I evaluate from 0 to 1. The leftover is minus 1/2, the integral of the cosinus. So the antiderivative of the cosinus is sinus. So I have 1/2 minus 1/2 of sinus of this dividing by this constant, but this is going to be 0. Right? So finally I have 1/2. So now Fn will be minus 2 dividing by n minus 1/2 pi dividing by 1/2. So then I have minus 4 n minus 1/2 pi. Alright? It's clear? So now I can have un, right? So un will be minus Fn over lambda n, so step 3. Which means that this is minus 4 over n minus 1/2 pi over this is a minus, so you have n minus 1/2 pi square. So basically what you have is 4 over n minus 1/2 pi to the power 3, right? And finally the solution is of the form u is the sum when n is going from 1 to infinity of 4 over n minus 1/2 pi to the power 3 sinus of n minus 1/2 pi. It's clear? Questions? It's good? You understand everything? So let me explain again. So here I can compute Fn, right? So Fn can be computed by taking the inner product of the source and the eigenvectors dividing by the eigenvector square. So you do all of those computations, what you get is, at the end of the day, minus 4 over n minus 1/2 pi. Alright? So now you have a formula for un. So you have un is minus Fn over lambda n. So this gives me minus 4 over n minus 1/2 pi over n minus 1/2 pi squared. Right? So which means that you have 4 over n minus 1/2 pi to power 3. So you plug everything, and this is the solution. You have the solution is the sum of this series. Alright? Questions? It's clear? So now you understand all of the 3 steps of solving boundary value problem using these eigenvalues and eigenvectors method, right? Yes?
Did you leave off the X and?
Yes, thank you. There's an X. Can you sign the back of the paper, please? So other questions? It's clear. Right, so I'm going to try to go over one more example so that you understand how this method works. So this is going to be something in the exam. So you won't have to solve boundary value problems using this kind of method, right? So the method is not that complicated, but the point is that you have to do all of the computation correctly, right? And those computations are, I mean, easy, but it is very easy for you to make mistakes. So you have to practice. All right, so example. So you have uxx is minus 1, and u0 is 0, u1 plus ux of 1 is 0. So the solution is on 0, 1. So basically this is Differential, and this is Robin. Right? So you can have a lot of several kinds of boundary value problems, but the same the only method that you have is eigenvalues and eigenvectors, right? So this is another problem. So the short term is minus 1, and at 0 you have Differential, at 1 you have Robin, right? So the first step is what? Eigenvalues, right? Can you say in the paper? Step number 1. So to find the eigenvalue, and eigenvectors. All right. So the problem will become phi xx plus lambda phi is 0 on 0, 1. And yes, I forgot to check the self-choice of the other problem. Right. So let me try to solve this one first, and after that I will go back to the other one and check both problems at the same time. All right. So now let us try to solve these eigenvalues and eigenvector problem. So you have phi 0 is 0, and phi of 1 plus phi x at 1 is 0. All right. Right, so this is the eigenvalues and eigenvector problems, right? So you have phi xx plus lambda phi is 0 on 0 and 1, phi 0 is 0, and phi 1 plus phi x at 1 is also 0. So this is the problem that we solve, right? And again the method is exactly the same. So what should we do?
Characteristic equation.
Right. Can you say at the back of the paper, please? So the method is exactly the same for all problems. So you have characteristic equation. Right, so you have x squared plus lambda is 0. All right? It's clear? So this characteristic equation has case number 1. Lambda is negative. Right? So when lambda is negative, what happens? two real roots, right? Can use both signs at the back of the plate of this. So you have two roots. So the first one will be square root of the absolute value of lambda, and the second one is square root of minus the absolute value of lambda, right? Right? So in this case, you have two roots. The first one is square root of the absolute value of lambda, and the second one is square root of the minus the absolute value of lambda, right? And then you have two solutions, which is u1 of x will be exponential of square root of lambda x, and u2 of x will be exponential of minus square root of lambda x. All right? Right, so basically the table that I gave you last time, yes?
Why does it need to be the absolute value?
Because this is negative, right? So you solve this, right? So you solve this, and you have minus lambda,
Right.
and this is the absolute value of lambda.
Right, but if lambda is negative, wouldn't it be positive?
So this is negative, so this is positive. Minus lambda is positive. So basically this is the absolute value of lambda. Right?
So in root 2, shouldn't that negative sign be outside of the radical?
The negative sign, yes, thank you. Can you sign the back of the paper, please? Right, so there's the root minus outside of the square root. Right? So because lambda is negative, you have two roots. The first one is square root of lambda, and the second one is square root of minus lambda with the absolute value, right? So then you have two solutions, right? So then you have a general form of phi, which is C1. C1 of exponential absolute value of lambda plus C2 exponential of square root of lambda x, right? So now I'm gonna check the boundary value problems, right? So basically, I found a general solution of this form, but I have boundary conditions. So this is boundary condition. So the first one is phi 0 is 0, which means that C1 times exponential of 0 plus C2 times exponential of 0 is 0, right? So this means that C1 plus C2 is 0, so C2 is minus C1, right? So the first boundary condition says that phi 0 is 0. Because phi 0 is 0, you have C1 exponential of 0 plus C2 exponential of 0 is 0, which means that C1 plus C2 is 0. So which means that C2 is minus C1. All right? So now, I'm going to check the second boundary condition. I have phi 1 plus phi x of 1 is 0. So now I have to compute what is phi x, right? So phi x will be C1 square root absolute value of lambda exponential square root of absolute lambda minus C2 square root of absolute value of lambda exponential minus square root of lambda x. All right? It's clear? Questions? Yes?
Did you mean C1 instead of C2?
What?
C1 instead of C2?
C1,
I did minus C2, but did you mean minus C1?
minus C2 because here I take the derivative of this one.
Oh,
So I have minus square, minus is outside, right? Right, so what is it? So I have exponential minus square root of lambda x prime, and this gives me square root of lambda exponential of square root of lambda x. So in general, you have exponential of ax prime will be a exponential of ax. All right. So can you sign the back of the paper, please? So now you take the derivative. So what you have is C1 square root of lambda exponential of square root of lambda x minus C2 square root of lambda exponential minus square root of lambda x. Right? So now I'm gonna plug phi1 and px1 there. So I have phi1 is c1 exponential of square root of lambda x plus c2 exponential of minus square root of lambda plus c1 square root of lambda exponential square root of lambda minus c2 square root of lambda exponential of minus square root of lambda. Right? And this is 0. Right? So I replace 1 here, right? So when I replace 1, I have c1 exponential root of lambda, and I have c2 exponential of square root minus lambda because x is already 1. I replace 1 here, so I have c1 square root of lambda exponential of square root of lambda, which is here, and minus c2 square root of lambda exponential of minus square root of lambda. Right? So x is all 1. It's clear? It's clear? So now I'm going to use the fact that c2 is minus c1. Alright? So what happens? So when I use c2 is minus c1, I'm going to have, so I have c1 exponential of square root of lambda minus c1 exponential square root of lambda, and then I have c1 square root of lambda exponential of square root of lambda, and I have c2 is minus c1, so I have c1 square root of lambda exponential of minus square root of lambda, and this is 0. All right. So the first step is you compute phi x, phi and phi x. You replace the value 1 there. So in the first step, I have this formula, right? The second step is to replace c2 is minus c1 into this formula, and have c1 minus c1 exponential minus square root of lambda, c1 of this plus c1 of this. All right? So which means that c1 times exponential of square root of lambda minus exponential minus square root of lambda plus square root of lambda exponential minus square root of lambda plus square root of lambda exponential minus square root of lambda, and this is 0. Right? Clear? Which means that because this term is not 0, so c1 is then 0, and then c2 is also 0. Right? So you have a trivial solution, and a trivial solution is not an eigenvalue, eigenvector. So phi is then 0, a trivial solution. Not an eigenvector. Alright? Screen questions? So for this kind of problem, it's a little bit you have to do this computation, but it's not that hard, right? So again, I explain from the beginning again. So because here, when lambda is 0, you have 2 real solutions, and the 2 real solutions give you 2 exponential. So what you do is that you replace, you take a linear combination of the 2 exponential, right? And now you take phi x, which is this one. Remember that here you have a minus, that is coming from this minus, right? So now you replace phi 0 to be 0. So when phi 0 is 0, this is going to be 0, which means that this one is 1. This is going to be 0, which means that the whole thing is 1. So you have c1 plus c2 is 0, which means that c2 is minus c1, right? So this is the first thing that we have, which is very important. And the second one is phi1 plus phi x is 1. phi1 of phi1 plus px1 is 0, right? So the first thing I do here is I replace 1 to phi and phi x. I get this formula. This is a little bit complicated, but the solution is always 0, right? So I have this complicated solution. I replace C2 to be minus C1. So here I have C1. So this C2 will become minus C1. This C1 is still C1. This minus C2 will become C1, right? So everything is C1 now. So I can put C1 outside as a common factor. And then I multiply that with a bunch of things inside, right? But this is not 0, which means that C1 has to be 0, right? If C1 is 0, C2 has to be also 0 because C2 is minus C1, right? So which means that phi is 0, and this is a trivial solution. So a trivial solution is not an eigenvalue, an eigenvector, right? Important thing. Right, so 0 is not phi is equal to 0, is a trivial, so this is Riemann. It's not it's a trivial solution. So this is not an eigenvector, right? However, if lambda is 0 and phi is different from 0, right? Lambda is 0 is still an eigenvalue. Right? Yes?
Is our phi is a function?
Phi is a function.
Yeah.
So this is the 0 function. This is
Okay. Because you say phi equals 0, so like phi at, you're saying
So-
at all values equals 0?
phi 0 means that phi x is 0.
Okay.
So phi, a function, the 0 function means that phi x is 0 for x.
Got it.
Right? So this is a 0 function.
Gotcha.
Right? So the 0 function is a trivial solution. But so it's not an eigenvector. But if lambda is 0, this is a number. So lambda is a number. So this 0 is a number. But if for lambda is 0, you can find phi which is different from 0, then lambda is still an eigenvalue, right? So you don't allow the 0 function to be an eigenvector, but you allow the 0 value to be an eigenvalue. All right? So it's two different stories, right? So this is case number 2. So you have lambda is 0. So you have the problem phi prime 0, phi 0, and 0, and phi 1 plus phi x at 1 is 0. All right? So this is something that we do all the times. So phi second is 0. So phi second is 0, means that phi x is ax plus b. Alright? So phi 0 means that b is 0. So phi 1 plus phi x as 1 will be a plus b plus a is 0. And because b is 0, so a is also 0. So phi is 0. So this is again a trivial solution. And this is not an eigenvector, right? So again, the second case is always the easiest case when lambda is 0 with this boundary condition, right? So phi second is 0. So we know we solved several times this problem. And so phi has to be a linear function. So it is ax plus b. Right? So you have a Dirichlet boundary condition at 0. So you replace 0 here. you have B is 0. All right? So you replace 1. You have phi1 plus phi access 1. So phi1 is A plus B. Phi access 1 is A. So you have 2A plus B is 0. But A is 0, so B is 0. B is 0, so A is 0. So which means that you have a trivial solution. So again, a function which is 0 is never an eigenvalue, eigenvector. But the number 0 can be an eigenvalue, right? Yes?
So when we're solving these problems, if we do one of the cases and it's not 0 and it's not trivial, we stop there and then we have to keep doing the other 3 and prove the.
No, you have to do all of the 3 because so you for instance at here you find one eigenvalue and eigen vectors, but maybe in the last case you can find others, right? So
Okay.
there are plenty of eigenvalues and vectors. So you have to go through all of the cases to find all of them.
Gotcha.